All right, guys. Welcome back to episode 29 of Coding Until I Get an Embedded Internship. So it's almost been a month. Tomorrow's the last day of May, so that's pretty crazy. So we've been coding for like around a month now, for like 3 hours. I 1 to 3 hours. I find that pretty good progress. I think like I didn't expect to make so much progress in the time I did. Especially like first things first, I complete my first project, and then now I'm like on my way to learn more about embedded and stuff like that. So yeah, that's great. Um, so last time we covered the touch sensor interrupts. I still got to figure out polling. I think I'll do that a different day though. I think I'll do that a different day. 'Cause, yeah, it's I tried working on it last night a little bit, like 30 minutes, not much because I don't have time last night. But yeah, it's interesting. I don't know why, because I think my code is correct. It's just something, and I don't want to ask like ChatGPT or whatever, because like I kind of want to figure this out on my own. You know what I'm saying? So yeah, I will. Yeah, so that's it for yesterday. Today I actually don't know what I want to do. I was thinking like doing more communication protocol stuff, but at the same time, like I also want to figure out Wi-Fi. Like, so like for example, let's do uh, like I squared. There's the YouTube channel, right? ESPIDF. Like this guy. This guy makes a bunch of good videos. I will. Sorry. Wait. There's two videos here. 11. It's projects. It's the series. Oh shit. Okay. Close this. So we did this. We did this. We did this. ADC. I didn't do ADC yet. DAC or ADC. I don't. Sure about that. Timer as well. We can maybe work on ADC today. ADC, and I think it's one of the core topic we should probably learn. So, yeah.
This is the fourth video on my ESP-IDF series, and in this video I'll be talking about how you can use ADC
Okay.
or analog to digital conversion of the ESP32 to read analog input from different sensors or modules. Analog to digital conversion, or ADC for short, is the ability to read a voltage level between 0 and a maximum.
Yeah, okay. So, like, audio waves, for example.
The ESP32 has its own ADC integrated on the chip. It has two ADC units and supports a total of 18 pins. You should check the pin map of your own ESP32 that you own to see which pin can be used for ADC. It should have the tag ADC on it. Unlike the legacy ADC driver, ESP-IDF from version 5 and beyond has two modes. One-shot mode, the ADC conversion only happens when you instruct it. If you want to get the output 5 times, you simply call it 5 times. Continuous mode, where ADC conversion is repeated automatically at a defined rate. You can still use the legacy API and run older code, but this focus on the newer version. I'll be only talking about one-shot mode in this video. When you are working with the ADC pins, they are mapped to different channels as shown here. The first ADC unit has 8 channels and the other has 10 channels. If you can't find which pin corresponds to which signal name, you can look it up in the detailed pin list that I put in the description. Now I will move to some concepts you should know when working with ADC. The resolution of the ADC provided by ESP32 is 12 bits, which means that the measured voltage level is between the value of 0 and 4095. However, you can change the resolution or bit width used in your application from 9 to 12 bits. The attenuation of ADC refers to the voltage scaling factor that can be used when measuring voltage levels beyond 0 to VREF. VREF is the reference voltage used internally by ESP32 ADC. It differs from chip to chip, but the median is 1.1 volt. Furthermore, we can also use a calibration driver to get more accurate results. As I've said before, different ESP32 chips may have different reference voltages, and thus setting up calibration can minimize the effect of this behavior. The next part of this video will be a brief walkthrough of the API. Note that we are using one-shot mode in this video. We first include the necessary header files, then we create a handle where we have to specify the ID, which is either ADC1 or ADC2, and whether we use ULP or ultra-low power coprocessor in our project. You can also adjust the clock source, but normally we just use the default one. Then we create a channel configuration with its bit width and attenuation value. We call ADC one-shot config channel to apply it on a specified channel. Note that you can apply the same config with the same handle to multiple pins or channels. Once done, we can get the raw reading of the ADC. The relation between the ADC raw result and the voltage reading one channel have to optimize the effects may have different 0.1.
Oh god. Oh god. Oh god. Okay. What is sorry. So what Alright guys, sorry about that. -1 dB. Okay, so resolution.
Take charge of your health with the
Oh, nope. Oh.
Hello friends, welcome to my channel, and today we will discuss about the resolution in ADC. This is very important topic of ADC and it is also asked in interview and mostly in telephonic interview it is also asked. So what is the resolution?
Yeah, let me watch this video. Seems more detailed, 18 minutes rather than just 5, like 7-ish minutes, I think.
Whether it is sound, images, distance, time, voltages or currents, we perceive our world in analog dimensions. Nevertheless, we also live in a world of numbers, arithmetic, text and symbols. If we want to calculate with analog values, we must first find a way to make them countable. So today we want to talk about these components that convert our analog world into countable digital values. We want to talk about analog to digital converters, or short ADCs.
Damn, this is like loud.
An ADC measures the ratio of an analog input value to a reference value and expresses it in the form of a digital value. For this purpose, the possible range of the input variable is subdivided into n equally sized intervals.
N equals, you know.
In the next step, each of these intervals is assigned to a certain value. We therefore have two steps: quantization and coding. When an analog value is quantized, there is always an error which cannot be avoided. It's called the quantization error, and we discuss it a little later. First, we want to have a look at this simple example of how the process of digitalization works. Here we take an analog signal that has an infinite amount of intermediate values and map it with only 8 different digital values.
Oh, this is the resolution?
These 8 values give us a so-called resolution
Okay.
of 3 bits.
Okay.
In other words, the resolution defines the smallest change in the input value that the converter can still distinguish. This smallest change is called least significant bit, or LSB. It is defined by the full-scale analog input range divided by 2 to the power of the number of the bits. If we take the middle of one quantization interval, we have to change the input value by at least 1/2 LSB to get to the next interval. We can therefore define an important characteristic, the transfer curve. The transfer curve shows the analog values of the input on the x-axis and the digital values of the output of our ADC on the y-axis. Some ADCs can handle positive and negative input signals and are therefore called bipolar. To keep things simple, we focus on unipolar ADCs with only positive input values. Ideally, the transfer curve should look like this. But as we will see, a lot of errors can occur in the conversion process. So let's focus on this curve for a while and see what kind of tragedies can happen. The first error that commonly occurs with ADCs is the offset error. It is defined as the deviation of the actual transfer curve from the ideal transfer curve at the
Sampling
zero
error.
point of the analog input value.
Use filters.
The offset error occurs as a constant absolute error for each, means that the possible range of an input variable is subdivided into n equally spaced intervals. The number of intervals is called resolution, sampling depth, or bit depth, and, as the name suggests, it is usually given in bits. With the former example of 3 bits resolution, we get a total number of 2 to the power of 3
Digital communication.
intervals. But for AD conversion, it is not only important with how many bits we quantize our analog
The
signal,
beats.
it is also important
That's
how
like,
often we do it.
this guy's the most German guy I've listened to.
Literature differentiates between 2 similar sounding expressions. The first one is sampling depth, which is the number of quantization intervals. The second one is sampling rate, which is a value for the number of conversions per second.
At Wayfair,
Oh my god. I hate YouTube ads. It's like they just come out of nowhere. You should get an ad blocker or something.
Basically, an ADC does both value and time quantization. In the next videos, we will learn that both values are important and which one is most important with a
Okay, in this video, never mind this video. ADC, how does ADC work?
minute range.
DAC. So this into 10 divided by 2 to the power 5 volt. So if the change in the input signal is less than equal to bits and the reference volt sampling theorem, the sampling rate
Hello, and welcome back to the Learning Circuit. I'm Karen, and today we're going to learn about analog to digital converters.
This seems like more EE focused, but I just want like a general overview how it works. Like, yeah, like I know what Nyquist Shannon is. Like, it's pretty important, but like they don't.
Serial data out a single output pin. Binary starts counting at 0, but are most commonly 10, 12, 16, or 24 bit. Looking at the waveform of an analog to digital signal, an analog signal would have a smooth, continuous slope representing how the signal can be infinite values between 0 volts and the maximum voltage. The waveform of a digital signal changes in steps, with a finite number of steps equal to the ADC's resolution, divided evenly between 0 volts and the maximum voltage. The signal change at each step goes low to high or high to low. ADCs can convert analog to digital signals in a variety of ways. In the first type of ADC, we can see how a comparator is responsible for each step change.
Ooh,
Previously, we've learned that a comparator has 2 inputs.
digital.
If the
Ooh.
positive input is greater, the output is a high.
Yeah, I digital. I've definitely used these before in my lab.
The analog input wave is converted to a 3-bit digital wave. This style of ADC is great for how fast and efficient it can convert the signals due to its parallel processing. However, given the large number of comparators needed, and since each bit requires its own output pin, chips can quickly become large and expensive to manufacture. To solve the problem of requiring an output pin for each bit, rather than having numerous parallel outputs, many ADCs run the output signal through a shift register, which then sends serial data out a single output pin. The next style of ADC is called a digital ramp or ramp compare. With this style of ADC, A free-running binary counter produces a sawtooth wave fed into a digital to analog converter. The sawtooth signal gets compared to the analog input signal, and when the signals match, the corresponding binary number is output, the ADC's timer resets, and the sawtooth starts over. The sawtooth always starts from 0, so the lower the signal, the faster the signals match, but the higher the signal, this inconsistency in update frequency can be problematic in certain applications. The next type improves upon the ramp model, being slightly faster due to its special counter circuit known as a successive approximation register, or SAR. This ADC starts with its most significant bit, comparing it to the amp count. But instead of 8, 12, 16,
Okay.
or 24 bit. Note here, the resolution difference in 80 pixels.
Okay, so, okay. I think I understand kind of how it works.
Cool. Furthermore, we can also use a caliper.
Oh, okay. So you sample it. You sampled the analog waveform. It's okay. So of course it needs to be Nyquist rate. So 2 times the highest, two times the bandwidth, or 2 times the highest frequency component in the frequency domain. Signals and systems coming in clutch. Like one continuous range of analog voltage is divided into finite numbers of levels based on the resolution. Based on the resolution. Okay. Okay. All right. So, I guess to summarize. So, the way ADCs work is essentially they just. I think I covered this in computer organization too, but I just didn't cover it resolution. So, you'll just sample. ADC will just sample at a certain frequency. That frequency, of course, needs to be in the Shannon-Nyquist. Needs to be a Shannon-Nyquist frequency. So that means either 2 times the bandwidth in the frequency domain, or 2 times the highest frequency component in the frequency domain. Once you get the bandwidth, once you get the sampling frequency, you can sample the analog waveform, and then each of the sample points will be encoded with a certain discrete value or bit, or aka quantization levels, right? And then essentially the resolution will tell you the range of the y-axis, or like the voltage levels. Tells you the. Okay, all right. Oh, sorry. No, sorry. Analog devices has a good article on this. Great. So we've done that. So let's move on then. Okay, so let's look at the video. Well, okay, continue on with the video.
Calibration driver to get more active is one point. Volt.
Okay, so what's the VREF? What is VREF of ESP32 room? Okay, ESP room data sheet. Let's look at the data sheet. Oh shoot. What the heck? Oh, this is an old design. There's no information here. But I think it's 3.3 volts. But I still want to verify it just in case. Table 10 ADC calibration values. to digital converter. All right, so I guess attenuation describes the yeah, it will just describe like okay. It'll just describe the effective measurement rate. And if you exceed that effective measurement rate, then you'll get some scaling. Okay. Let's go to ADC characteristics, sampling rate. What is kilo samples? KSPS, 2 hertz. A sample maybe 8 bits, 16 bits. Yeah, okay. This depends on the resolution, I'm guessing. LSB is like the difference.
Furthermore, we can also use a calibration driver to get more accurate results. As I've said before, different ESP32 chips may have different reference voltages, and thus setting up calibration can minimize the effect of this behavior. The next part of this video will be a brief walkthrough of the API. Note that we are using one-shot mode in this video. We first include the necessary
You sample at 2x the sampling rate, And you give it, quantize it, you quantize it. To encode a digital. Once you encode that digital value, okay. That's how ADC works essentially. So you sample, quantize, and then encode. Okay.
To multiple pins or channels. Once done, we can get the raw reading of the ADC. The relation between the ADC raw result and the voltage level is presented in the formula. But again, we can perform further calibration to get a more accurate result. We create a calibration unit handle and then configure a fitting scheme. The curve fitting scheme is a result.
The ADC raw digital reading result times the voltage max. ADC attenuation, okay. Maximum of the output. Okay. Bit width.
We create a calibration unit handle and then configure a fitting scheme. The curve fitting scheme is available for the ESP32C3 and subsequent products, and we would use a line fitting scheme in this example. The configuration must match what we've configured for the ADC channel. After this, you can convert the raw reading to a voltage level in millivolts. Let's apply this to measure ADC input from a potentiometer using ESP32. Wire the left pin to 3.3 volts, the middle one to pin IO26, and the right one to ground. We must first change our C makeless file to include ESP-ADC, as one of the can also be used as the 9th channel of ADC Unit 2. We then configure the channel to have a bit width of 12 bits and an attenuation value of 12. The default bit width should also be 12 bits. Of course, as a demonstration, although they are not going to be called here. Flashing the code to our ESP32, we can see that when we rotate the knob of the ESP32, the value displayed on the terminal also changes. The value of the raw reading ranges from 0 to 4095, which is also when we can't know.
Yeah, okay, so you have your, yes, so again, attenuation will just effectively scale down any analog input that exceeds the reference voltage. But how much it scales down, I'm not, the video, I'm reading a data sheet right now, it doesn't really, it says there's a table of ADC calibration results. Okay. Okay. Okay, so let's get let's think of something. What's the application of this? I mean, the easiest application I can think of is just using audio. So like you use a speaker, you put in use ADC to convert values. But I don't have a speaker right now, so I can think of some use of it. What? Okay, let me watch. I'll just I'll do it without the potentiometer.
Wire the left pin as one of the components that.
So let's get working on this then. I already saved this, so don't worry. Okay, so let's get started. Okay, let's see, what do I need to string? Okay, so what drivers do I need? I probably need I definitely need the ADC driver, so that's probably ADC.h. What else do I need? It says. Oh, he's using a different type of. That's interesting. You don't. So wait. So what's even in this thing? ADC. Let me consult the documentation. Oh my god. Shoot. Oh, never mind. Okay. So let me look here. Let me look at the. Wait, actually, I might have a potentiometer. Wait, now that I think about it. Yeah, let me find it. Bunch of caps, the ICs, digital stuff. All right, I got it. Though, don't know if it's a. It is what it is. There's too much extra stuff on this breadboard that I'm not going to need. So let me just check out the jumpers. I'm not going to be needing any of them. Project. Okay, so let's get to. Okay.
Result. We create a calibration unit handle and then configure a fitting scheme. The curve fitting scheme is available for the ESP32C3 and subsequent products, and we would use a line fitting scheme in this example. The configuration must match what we've configured for the ADC channel. After this, you can convert the raw reading to a voltage level in millivolts. Let's apply this to measure ADC input from a potentiometer using ESP32. Wire the left pin to 3.3 volt.
So you wire the left pin to 3.
The middle one to pin I26. And the right one to ground.
Okay. So let's do that. Let me configure this. Okay. Okay.
We must first change.
Okay. Probably use longer wires for this. So let's have. So first 3.3 volts. Let's connect that to the. Let's connect that to this one, right? And then we'll analyze from the middle. Okay, this is good. Let's go to pin 26. GPI 26. Okay, wait, let me get. Oh, never mind. Already have a jumper wire here. So what's gonna be? So then the right side of the potentiometer is back to ground, right? So we're creating a closed loop connection here, where we're analyzing the. Oh, this jumper wire is like faulty. And then we. Actually, I'll just. I don't know what I'm doing here. I'll just show you the setup. This is what I'm doing right now. So I get what he's trying to do here. The use of the potentiometer here is just will just be to apply some voltage on the resistor. We can adjust the resistance, the potentiometer. Shoot, what's happening here? It's not working. Why is this like, okay. Should I just get a jumper wire? Just a ground, and we connect it to ground. Okay. So just to finish off the closed loop. Okay, guys, let's continue on. So.
D channel of ADC unit 2. D. The second unit.
Why are some people like this? Okay. Shoot. There's other components on my breadboard which I don't want to touch. Okay, so the guy in the video, he's using a different library. He's using ESP ADC /ADC one shot.h. Not continuous, sorry. One shot. Okay, so just like, you know, a lot of stuff here. Is this in the documentation here? The thing is, it's not in the documentation, which I find... oh, we're looking at an older version. I'm like... ADC, ESP32. How many, bro? There's like so many versions here. I need the real version. I need the latest version. This. Yeah, so we were looking at mainly a legacy thing. So what version are we? 5.4.1. I'm gonna memorize that. sorry. Oh my, okay. So we were looking at old version. Okay, so anyway, let's begin. So the first thing, let me read the documentation here, and then I think he'll probably do the same thing, right? Under normal one-shot mode. So let's do that first. Program has commenced. Let's do ADC one-shot, unit handle T, ADC one handle, ADC one shot unit okay, that's init configuration, initialize configuration 1 equals. Let's go to definitions. You have the unit ID, the clock source, and then the ADC control ULP. Controlled by ULP. What is ULP? The ultra low power coprocessor is a simple FSM which is designed to perform measurements using the ADC temperature sensor and external I2C sensors. Well, the main processors are in sleep mode. Okay. What the heck? This is super weird. What the fuck? Why does it keep doing this? Why is my monitor like this? ADC unit. What ADC unit are we using though? Let me see.
ADC reading task. We first set up the ADC handle unit to use this.
Okay, and then let's set this to null. Let's see. So he's doing the exact same thing, and we're using ADC handle, ADC unit 2. What is unit 2 again? Let me look at the guy's sheet. Okay, we're using unit 2, GPIO 26. But wait, we're on 26, not 20. That's kind of
Result. We in millivolts. The middle one to wired to 3.3 volts. The middle one to pin IO 26.
okay.
And then we include the
Okay. Then let's do alt mode. Clock source. So we don't specify the clock source. We just, okay, we're just using the default clock source. Looks like so it'll. Okay, so we're just using the APP bus. We're just using the APP clock. Then, okay. Okay, next. I should probably do this more. ESP error check. And then let's put in, I think it's init config 1, right? Oh wait, no. Wait, it is init config 1, right? And then, yeah, and then handle. Putting the address of the okay. That's so we configure the init. Good.
default.
So we can either do bit width 12, right? So this is remember, this is the resolution, right? Or we could do ADC bit width default, which is the same thing as 12. Okay. And then what's the other one? The attenuation, right? The attenuation. Sure. D.at10 equals ADC at 10 dB12. So this is the maximum attenuation we want. Okay. Okay. That's proper. That's proper.
Bit width should also be 12 bits.
ADC one shade shot. What's channel 9 again? Shit. 25. I think he misspelled. Okay, I'll let the guy know in the comments or something like that. But it's a small error. Okay, ADC channel 9. So that's going to be GPIO 26. So remember, so ADC channel 9 equals GPIO 26. So, and then, okay, and then we put the address of the config. The equal sign there. That's good. And we had the calibration handler. Oh, sorry, ADC1 handle. Okay.
Then we create a line-fitting calibration scheme with our configuration matching that of the previous ADC channel configuration. In our while true loop, we repeatedly measure the raw ADC reading and the voltage level after calibration, and then display them to the serial monitor. I'm going to put the delete functions to free the resource as a demonstration, although they are not going to be called here.
And then what's let me figure this out on my own. This is the handle, this is the channel, and this is the pointer to the whatever you want to read into. So let's say, I don't know, let's say you have int ADC potentiometer read. Okay, so potentiometer read. So first we need to put in, we have the handler, so we know what the handler is, ADC handle. And then we gotta put in the channel. So we know what the channel is. So we know it's channel 9. And let's put in the pointer with the potentiometer read. Yep, that's exactly what I want. And then print F. We don't use serial here. We don't use serial, which is kind of weird, but I'll just go with it, I guess. We don't need to do a pointer. It's already okay. It's already modified, right? We don't need to star it. That makes no sense. Indirection operator. We don't need to use an indirection operator. Because that'll just change the value itself already inside the pointer, inside the function. Sorry. Measurement, and then ESP. Okay, and so let's just good.
ESP32, we can see that when we rotate the knob of the ESP32, the value displayed on the terminal also changed. The value of the raw reading ranges from 0 to 4095, which is also when we can't no longer change the knob to either the right or left side. The maximum voltage level after calibration seems to be 3.1 volts, which makes sense considering that we give 3.3 as the source.
All right, let's read. Let us build this. Okay, so a bunch of problems here. So number 1, I don't know what the heck that was. Kali config. Also, I forgot to calibrate. I forgot to. Hold on. Yeah, I forgot to. Kali handle. let's we can. No. Never mind. Let's not do that. Let's. Okay, it compiles. It compiles. Okay, there you go. So let's yes. What the heck? Watchdog timer. I didn't enable any watchdog timer. Okay, wait, hold on. So wait, what the heck was that? I don't know. Let me use the washroom real quick. I'll be right back. Okay, I'm back. Sorry about that. Anyway, so yeah, it was definitely working. We should also maybe we should add like a delay or something. Let's just do vtask delay. Let's do like 100 or 1000. I don't. I think 1000 is probably more better. Actually, no. What am I doing? No. Let's build in Flash. Yeah, so this is legacy. This is like legacy stuff. ADC.h. This is straight up legacy. Yeah, 1000 is way too slow. Let's get out of here. Let's do 100. Okay, that's good. So let's say you can see if I adjust it, we are decreasing. here we're getting 0, raw ADC measurement 0. Does the resistance? Definitely. Okay, yeah, so that makes sense. If you would turn it to the left, it will increase the resistance, right? So if you turn it to the left, it'll increase the resistance. So if that is the case, then it will effectively allow voltage to run through, and just thus a current. There will be bigger voltage drop through the to the resistor. But if you were to change it the other side, then this basically acts as a short circuit, essentially, because it's connecting. You're decreasing the resistance to a point where it's emulating the ground, right? Yeah. So if it acts like a short circuit, then it'll have 0 voltage drop through the resistor. All right, great. So there you go. Yeah, that's great. The raw ADC measurement is 0, because I guess that's how we encoded it to be. Like 128 volts is say that's like not 128 volts. That's impossible. 120 millivolts, right? Yeah, it's definitely in millivolts, because let's just say anything I think is like above 50 volts will literally kill you. So like, yeah, and obviously I'm not dying from touching a goddamn potentiometer. So yeah, my thing's not on fire, thankfully. So yeah, if we turn it, so that's 3,103 millivolts to 3.13 volts, which is logical. All right, great. So obviously now let's say we reduce the okay, let me comment about this. This guy, he messed up the pin measurements. Okay. All right, great. So let me do a little experimentation here. So number one, right? Let's change up. And also, guys, by the way, today I'm gonna be ending in like 1 hour. So like 1:40. So 1 hour and like 2 hour 45 minutes, I think. So like by the end of 1:50, I think I'll probably end it. But anyway, yeah. So first, instead of using channel, sorry, let's keep the unit and channel the same. Okay, number one, like, what's the difference between these two channels? Oh, okay.
Files, one project. Then we see ImConf ADC, the relation between the ADC raw result of.
Okay. So that's the difference between the two channels. Sorry, two units, right? Unit 2 can't be used when Wi-Fi is being used. Okay. We'll create the handle, the config, create a new unit, channel. We configured the channel, the bit width, the attenuation. All right, good. So now let's okay, so let me write this down. Okay, so if we use, let's say we use 12 bits, 12-bit resolution / bit width. And then so at 240, 257-ish, right? 247. So that's like half, right? So let's look at it at half. So it's like 240, like 248-ish. And like it'll be 1761 volts. Okay. Now let's change the bit width to ADC bit width. Let's change it to instead of 10 bits. 10 bits instead. Yeah. This is definitely an enum. Yeah, it's definitely an enum. Okay, it's still fairly accurate. It's still fairly accurate. Now, what if we reduce what's the maximum bit, what's the minimum bit width? Let's see here. What's the minimum bit width?
Deep application.
What is the minimum bit width? Like what is like what what is
32 has it. Video for one is between accurate.
Bro, what?
Convert the raw reading to a voltage.
It doesn't say. What is the minimum bit width? Is 32. I guess. Wait. I can just search it. Oh. It's 9. It's 9. 2 to the 9. Yes. Let's see how. But it's not that significant unless. Yeah, it's fairly accurate. Even if you use lesser bit width, it's fairly accurate. Now, my next question would be the one-shot config, the calibration handler. I need to know that. What's the calibration handler do? Calibration. Let me read the documentation. There's a whole page on that. Okay. Oh, okay, right here. Perfect.
Result. We create a calibration unit handle and then configure a fitting scheme. The curve fitting scheme is available for the ESP32C3 and subsequent products, and we would use a line fitting scheme in this example. The configuration must match what we've configured for the ADC channel. After this scheme,
Okay, so what this does is this just reads it from the channel, and this just calibrates it to read the raw voltage. Okay, and we use a line fitting scheme, which is just going to be a linear pattern.
in the formula. You can apply the same config with the same handle to multiple pins or channels. Once done, we can get the raw reading of the ADC. The relation between the ADC raw result and the voltage level is presented in the formula. But again, we can perform further calibration to get a more accurate result. We create a calibration unit handle.
Okay, so okay, so next one. Ah, okay, so continuous mode is more like audio application, right? So you sample it at a certain rate, right? Okay, so audio, like audio. Let me read the documentation for a continuous ADC mode. Um, all right. So, okay. What else is there to do? We could try continuous mode now, but I don't have a speaker, so that's not particularly useful. I think that's maybe for next time. Yeah. Yeah, I might do something with audio then for my next project. Like using ADC for audio and stuff. I think that's definitely within possibility, in the realm of possibility. Oh. Let me read the documentation a little bit more further real quick. Okay, let me read this. Okay, let me just show. Okay. So you got the maximum buffer size. So I think this is the FIFO, right? The input FIFO. So person FIFO audio, right? Input FIFO. It's a buffer, yeah. It's a buffer that stores audio data in the queue. Yes, this is the input FIFO. Set the maximum. Set the size of the ADC conversion frame in bytes. So there are conversion frames. Conversion results. So basically, in each conversion frame, in each sample, I'm guessing. Oh, not sample. Conversion frame. There's a certain amount of data you can set this take in bytes. After setting up the configurations for the ADC, call the ADC new continuous new. Okay. So just one. We can just put one. So configs. Sampling frequency. So it should be. Okay, good. That's how that works. And then so you use the shoot. And then okay, you set the continuous configuration up. That's great. And then you ADC control. And as you start the ADC so you trigger ADC continuous or ADC continuous now. So conversion done event. So that makes sense. That's logical. Okay, that's perfect. We can also add calibration if we want.
The first ADC.
Oh. Okay. All right, I'm going to take a quick break. Uh, when I come back, I'll cover DAC a bit. Does he have a video on DAC? He does. Okay. Oh, shoot. Yeah.
On ESPIDF. Question how DA.
All right. Be right back. All right, I'm back. Let's watch up. Let's finish watching this video and see what's up.
Welcome back to another video on ESP-IDF. Today we will be creating simple DC analog signal using the digital to analog converter, or DAC, of the ESP32. If you are switching from the Arduino, then this feature should be new for you as the common Arduino. Uno doesn't have DAC. As I've made a video covering ADC, and if you have watched it, the concept of DAC should be obvious to you, as it simply is the inverse of ADC. DAC converts digital values and then outputs the voltage level corresponding to this digital value. The resolution of a DAC indicates the number of possible output voltage levels. For the ESP32, it has two 8-bits DAC channels located in GPIO 25, channel 0, and GPIO 26, channel 1. But the
Okay.
The ESP32 S2, they are pins 17 and 18, respectively. This means that at the same time, you can generate two analog signals out of these pins, and it can output the voltage within the range of 0 to 3.3 volts, based on the input digital value varying from 0 to 255. If you have seen my video on PWM with LEDC, you may question how DAC compared to PWM if they can both output analog values. Let's say we want to get 1.6 volts out of ESP32. If we use PWM, then it is switching between 0 and 3.3 volts repeatedly, where 3.3 takes 50% of the cycle. DAC should output 1.6 volts directly. If you have noticed, then PWM requires its timer to count extremely fast. For example, to perform 16-bit PWM, the timer needs to count up to 2 to the power of 16 in an extremely short amount of time. DAC doesn't have this limitation, and it is the faster and more precise option. This makes it suitable for audio, video applications, signal generation, industrial control systems, or sensor systems compared to PWM. Coming back to the topic of using ESP32's DAC. In ESP-IDF 5.4, which is the current stable version, there are 3 modes of using DAC. Direct voltage output, or one-shot mode. This is pretty self-explanatory. Note that you can output even in ISR, or interrupt handler. Continuous mode, where ESP32 outputs analog values using DMA, or direct memory access cosine wave to generate cosine wave. Of course, you can configure the frequency, amplitude, or phase. This video only illustrates the basics of DAC, so I will not delve into the continuous mode, which is normally used for data transmission. If you are going to do audio-related project, my recommendation is that you should also take a look I2S, or inter-IC sound, peripheral of the ESP32. For transmitting audio data, you can use synchronous writing, which loads all of the data into a DMA buffer before transmitting them, or asynchronous writing, which transmits data asynchronously based on event callback. If you are going to build a wave generator, then use the cyclical writing mode, which converts data in the DMA buffer repeatedly. The API of DAC follows the same pattern as ADC, but is a bit more simple. You have a handle and create a new channel for it with a specified config. You can start operating on the channel afterwards, and don't forget to delete the channel after using it. This is pretty straightforward for the one-shot mode. But for cosine mode, you have to specify more parameters in the configuration, such as frequency. A minimum of 130 Hz and should not be more than 200 kHz. Clock source, a 10-wire A1 ground. So use a chicken so you don't have to replicate this. From my experience, you won't get the desired output. Portable oscilloscope.
With their portable oscilloscope. Oh, that's pretty crazy.
Create continuous mass functions in early form.
So what is he doing right now? He's using the one shot, right? One shot. But take a single digital value, then output the desired voltage directly. Yeah, okay.
Terminate it and switch to the cosine.
I don't have an oscilloscope, so I don't think I can do that right now. But I'll probably buy one. I didn't even know they had like portable oscilloscope. I wonder how those even work. Let me search it up on Amazon real quick. Oh my god, they're like 44. They're like $100. Oh, no, sorry, I'm looking at the wrong one. I think the one he has is like $44. That's actually not too bad considering the technology of an oscilloscope. But still, a little bit on the expensive end for someone like me. So I don't know if I'll get that, but it's always worth, always worth trying. You never know.
Oscilloscope.
Oh,
For a while, you will see the LED getting brighter until it reaches its peak and slowly dimmer to no light. Right now, we are getting a triangular waveform. After a while, it will become bright at a moderate level. And we know that the waveform is actually a cosine wave. Adjust the oscilloscope a little bit, and we can see it better.
I think this is literally the exact model he's using. I have it right here. Yeah.
Note that I use the probe on both the resistor and the LED. If you try to use it with the LED alone, the waveform will look distorted as you have to account for the voltage drop across the resistor. And that's it for this video. Due to my tight schedule, I can't release videos too often, but be assured that I don't intend to end this series yet. Thanks for watching and hope you can support me by subscribing to this channel and liking my videos. Or give me a small donation with the info in the description.
Oh, I might actually just give him a donation. Maybe like when I get my first paycheck. Oh my. This is he's from Vietnam. Oh, that's pretty cool. Yeah, I'll definitely send some money to him. Hopefully. Okay, so for DAC. No filter. No filter required. Okay. That's what PWM is. Okay. And also, yeah, okay. Oh yes, Class D amplifier. I I think I remember working on a project in university for some hardware design course about that. It's pretty sick. But you have to use a filter. That's the thing. Um, but it's kind of. But the thing is, like, I think, like, yeah, isn't actually never mind. Speed is important. For instance, to produce high fidelity audio. To pulse width modulation. Okay. Never. You need direct analog signal, precise. Okay. I could set up the DAC right now if I wanted to, but I'm gonna have to go soon, so I don't know if it's worth it. Actually, wait. I'll set it up. I'll set it up, but we might just might be like a little. Okay, let me pull up VS Code now. Yeah. Okay, let's get to work. Okay, so let's.
Demo prop LED channels so you don't have to rep two separate sine mode. and the result should be a triangular waveform. In fact, you in the one-shot mode, I gradually increase the output before decreasing it, and the result should be a triangular waveform. In fact, you can combine the one-shot mode and timer interrupt to create.
This doesn't work. No, it does work.
sine wave generator here until let's test the output when two.
Okay, let's see if this works. And I have to go. Implicit declaration. Oh, it's what is channel 0? $25 and $26. Okay, so let's get working on that. Oh, shoot. Oh, what the heck? That's kind of weird. Okay, I'm gonna have to go now, unfortunately. Yeah, I kind of just last minute this. Okay, I'll do this tomorrow. I'll finish this up tomorrow. I kind of just write the code, but I didn't really think about it too much. Shit. How do I cancel this? Control C? Control C maybe? Yeah, I don't know what the fuck is happening. Whatever. Okay, anyway. Let me just close this because I don't want to. Anyway, yeah. Okay. All right, guys. Thank you for watching today's episode. Today we worked on the ADC and a little bit on the DAC. Tomorrow we'll wrap up the DAC and then we will work on I squared C maybe? I squared C SPI spiffs, maybe. I might consider that spiffs. And then after that, I want to work on Wi-Fi. And that type of stuff. So yeah, alright guys, thank you guys for watching. Have a good day. See you guys later.